that comes up here. So my rough plan is today talk about section 1.6, which is very short, very straightforward, but some essential skills for after exam 1 for calc when we get there. Wednesday, no class, but I will record like a little lecture. I'll work through some problems and post that. And if you would check that out, that would be great. Or you could just try the problems and maybe you do great on them too. It seems like a lot of folks in here just start on the problems and crank them out and maybe have all of them done. even stuff we haven't talked about yet. And then next Monday would be just space to come in and work and catch up. And I could give you, if you would like a practice exam so you knew kind of, would that be something we would like? Yeah, cool. And then this exam will be on Wednesday, and it's very basic stuff, but I'll make a practice exam for us and get that to you with solutions. I think that probably everything up to this point is going to be pretty chill. It seems like everybody's pretty on board with everything. This stuff here is exponentials and logs, and that I feel like we might need some extra time in here to talk about. That's something that folks generally have trouble with. We don't do trig in this class, so congratulations, or I'm sorry, whatever you were hoping for. There's no trig component at all, so that's good. That's good news. And then we'll do this exam, and then the week after we'll actually start on calculus. So for some of you, this class is like way too slow, and I apologize, but I hope nobody's like miserable, right? And some of you, it'll be an easy A. Cool, happy to give you that A. I just don't want folks super bored. So, any questions or concerns or requests? Let's have a dialogue. What works for you? Does anyone need like more challenging problems? No one's making eye contact with me for that one. But I would happily get you some more challenging things if you would like, if you're feeling unchallenged. We good? Yeah? Okay, all right. I'll trust you and you'll tell me. Maybe you just want to tell me in private or something. Let's take a few minutes to settle in. Please. Take this time for yourself. You deserve self-care. We all do. We just don't do it enough. So we'll just close our eyes and notice what our bodies are feeling like right now. Wherever your mind goes, watch that. Noticing your feet, your legs, working up through your hips and in your abdomen. And spend a minute here when we get to our belly. How is your belly doing? Just notice without judgment. We keep a lot of things in that space. I know I do. And then moving up to the chest from the center, another place we keep a lot of anxiety and emotion. How's your heart doing? And let's just keep moving up. Check out your throat. get super emotional. Sometimes it's hard to speak. So things get caught up in our throats. The muscles are linked to our emotions. How's your throat doing? Then let's just end by noticing if we have an expression on our face. Or any tightness that we didn't even really realize we were holding there. Absolutely cool to feel whatever we're feeling. But what if we raise the corners of our mouth just a little and actually put a smile either on our face or in our minds? So if you don't want to smile, imagine smiling. Very good. Give yourself an intention for the day. What do you want out of this day? If you said mathematical understanding, I hope we can help here. Thank you, my friends. All right, so any questions over stuff that has been? And I guess that's up through 1-5. Is there anything you'd like to talk about from the past? And we will take time today to work so I can come around and help you if you're having troubles on any of the problems. Okay, all right, cool. Let's do some 1-6 stuff. And today we're talking about polynomials and rational functions. I hate that pen already. Better. I got a blackboard installed in my office. So sweet. You gotta come. Nobody from here ever comes to visit me in my office. Come visit me. I've got this sweet blackboard. And have you ever seen chalk pens? Oh my God, they're just so gorgeous. So yeah, everybody's kind of jealous. Everybody is jealous. Okay, so come on by. I'm just regretting that I don't have it here. And I'm just gonna kind of go through the basics here. We'll work some problems together, but just a little bit of refresher. If I have a function that is some power of x and there's some number in front of that, so this a sub n is a constant. And in fact, this one is called the leading coefficient because it's on the highest power of x. So that's how you know what your leading coefficient is. It might actually not be out front. The highest power of x might be mixed in with some other things. And I'm going to put variable here because it's not always x either. And then I've got a lesser power of x, and so I'm going to denote that as an a sub n minus 1. Notice this little subscript just says these are different numbers, and they're paired up with the power there. So if this stresses you out, this is totally good. We just want to notice that the power of x is decreasing, and we go all the way down to a first power, which we don't need to put the 1 on, and then a constant term. So this is the constant term. The degree of the polynomial is the highest power of the variable. So the degree, hello.
Hi.
The degree of a poly equals the highest variable power. And there's only a couple basic things that I want you to know about a polynomial. If I gave you an equation, I want you to have a sense in your head of what this shape looks like if we graph it. So, required skills. Here's what we need to know how to do. One is find the zeros of a polynomial. We don't need to get super fancy with factoring or anything like that. So there's a couple ways to do this. One is factoring. I'm not going to ask you to have super expertise in that, but if I give you something that's factored, I want you to understand how that relates to the zeros. So what do I mean by zeros? I mean the places where the graph crosses the horizontal x-axis. So we have x, and then f of x here. These are the zeros. They will become super important to us as we move through into calc. Find the zero, so that's one of the required skills. Number two is sketch a very rough graph. And there's two parts to this. After we found the zeros, what I want to know in here is where is the graph above the x-axis, above horizontal axis, and where is it below? So up here, this one is above these two zeros and it's below those two zeros, and then below and above on the ends. I just want to be able to have a sense of that, not the exact precise version of that. Cool, so where is that? And then what is the end behavior? And sometimes this is called tail behavior. And I'm going to write it in a super fancy calculus-y way. So i.e., what happens to f of x as x gets very large? And I'm going to show you a little notation here. X approaches infinity. This will become a symbols for us. In about 2 weeks, we will be doing this. So this just means x is approaching infinity. It's just getting bigger and bigger and bigger. But I also want to worry about the left tail end. And also, sorry, it's getting kind of crammed in here, as x approaches negative infinity. So you could draw a little picture up here. And this is x approaching positive infinity, and this is x approaching negative infinity out this way. Just good language. This is part of the thought process of calculus, thinking about as things move toward a certain value, what happens to the output. That's total calculus stuff. So if you notice on this one, let's come back up here, that this thing here, f of x, keeps getting bigger as x gets bigger. We have every reason to believe that thing just keeps growing. So I would use this notation. F of x approaches infinity as x approaches infinity. And then down here, we have f of x is dropping. So it's going to negative infinity as x approaches negative infinity. And this just means left. And this just means right. And I guess this means up, and that means down. So those are the things we want to deal with today. And let's just get an even more rudimentary fact about the basic shape we should expect. So here's kind of a useful fact. So that when you see a polynomial, you can kind of make a picture in your head. You might need more details, but you've got a hope of getting things done. So the useful fact is this. If p of x is an nth degree polynomial, that means it's got x to the n somewhere in it, maybe some constant in front. how many turns will it have? So for example, here's a 1 turn. What degree do you think that is? What could that be? 2. Yeah, I'm getting the 2, getting the peace sign. So that's a quadratic. What degree is that? 3. Yeah, don't go too far. We're just going up, just moving up a little bit. So notice here, I've got 1 turn. Here I've got 2 turns. So this is 1 turn. This is 2 turns. And this is quadratic, so this is degree equals 2. This is degree equals 3. It might not be this many, but there's the chance that that can happen. So what does a degree 4 look like? Well, it has 3 turns. So we could go like that, 1, 2, 3, or could go 1, 2, 3. So it changes its up and down direction that many times. And so, if it's an nth degree polynomial, it can switch direction 1 less time than the degree. N minus 1 times. And if that doesn't make sense, just keep an eye on this. And if you have these examples in your head, you've got a pretty good basis for understanding this. Rarely will we have a 4th degree polynomial, but what if we had like a 7th degree? So that means I could switch degrees, directions 6 times. 1, 2, 3, 4, 5, 6. So crazy. Could be wild like that if I had a 7th degree polynomial. And now we got to get more details to figure out where the humps are and some points. But that is a super useful fact. So let's go through this list and talk about how to find the zeros. So step 1 here is finding the zeros of a polynomial. So let's start with an example. Let's say I have f of x equals 3x squared minus 1. Oh my goodness. How do I find the zeros? What does it even mean to find the zeros? What does that mean? So yeah.
Find where x might be like on the graph.
Yeah, to find out where the output is 0. So yeah, there's 2 kinds of, yeah, absolutely. If I'm finding where x is equal to 0, that's the vertical intercept. That's just where I hit the y-axis. So, so yeah, we want to solve f of x equals 0. So here, that's 3x squared minus 1 equals 0. How would you solve that? How could you solve that? Let's talk about all the ways. Factoring might be painful. What degree is this? 2nd degree. Quadratic. How do we solve a quadratic equation?
We could complete the square. We could do the quadratic formula.
Oh, I love that. Thank you. Yeah, we could do all the quadratic shit that we just did last week, right? Quadratic formula. So, could use. Thank you, Lorelai. That's very helpful. Could use the quadratic formula. What else could I do? Let's say I couldn't remember the quadratic formula. What could I do? And the completing the square and all that stuff, definitely. We could do that by hand. What if I had a calculator? What could I do? I have a calculator, but no knowledge of how to do any of this stuff. What would you do? If I said approximate the solutions. Could use a calculator to do what? Just like think, how could you? Anna, did you have some for me?
I mean, I originally was gonna say if you like plot it on there, make the graph.
Get a graph.
Yeah, okay.
exactly. Yeah. So yeah, and I think a couple of you were thinking that and just not sure that's what I was looking for. So you could use a calculator to graph it and approximate where it crosses the horizontal axis. So you have to kind of trace on there. It's really painful with a calculator, but maybe not. Maybe it'll trace, it'll follow the graph. So for this one, we would have something like this. If I plotted out the graph, and if I looked at where these two were, I would see that this is approximately 1.732, a bunch of stuff. Negative, oh no, be much worse. It's 1 over the square root of 3. Square root of 1/3, negative square root of 1/3. And you would put that into your calculator. I don't know what you'd get. Could somebody actually do that for us, please? What is that approximately? I'm gonna try to work it out, but I don't think I can. I don't know how to do it in my head. It's approximately 1 over 1.732, but that I can't do. And I'll just wait for someone.
0.577.
That was it. What was that, Jack?
0.577.
0.577. Thank you. So I would see roughly 0.577 here, and I wouldn't know the truth unless I knew how to use the quadratic formula. But I get a sense, and we're good. So the other way is to factor. To factor the polynomial. Now, this one here is not going to factor nicely. It could factor, but in this class, I'm not going to ask you to factor a lot. That's not one of the skills we're required to learn here. But I could factor. Could factor completely. And let me go ahead and do that for this one. And actually, does anybody know what the factorization could be here? It's kind of weird. It's not the kind we're used to. Ooh. What could we do for factors? A little funky. So how do you go backwards, right? You would FOIL backwards. Let's just kind of work it through together. If I FOILed, what would the L need to be? -1. So I need a 1 and a -1 in there somehow. And then that way the L is equal to -1. Cool. I need the F to equal 3x squared. But I also need the O and the I to cancel each other. So let me just kind of get you the answer in here. Square root of 3x plus 1, square root of 3x minus 1. But that's, I've just done that kind of stuff a lot. That's painful. And maybe you wouldn't even get there if you saw that. Usually we expect factors to have nice integers as their coefficients. But I could do that. And then once I have that, the zeros, if this is equal to 0, so this equals 0 when x equals -1 over root 3, and this equals 0 when x equals +1 over root 3. So I could get the same answers lots of different ways. Once I have those, I can get a better idea of the picture. Let me show you what I mean. So once we have the zeros for, let's call it P of x, we can determine where it's above and below the horizontal axis. And get a better shape of it. And let me show you how to do that. So here's the plan. Plan is this. on a number line, on a line, maybe a part of a graph, mark off the zeros. So we have to do the zeros part first. Let's just come down and do it. We can do it here, we can do it on just the line, all good. But let's say I've got a 0 here, here, and here. And I figured that out somehow. My next step is to notice that the zeros create regions. 1, 2, 3, 4 different regions. And what I'm going to do is grab a point out of each region and test it in that original function to see if I'm above or below the axis, positive or negative. So that's the plan. On the line, mark off the zeros, then test the sign, S-I-G-N, that's all I care about, of P of X in each region. So if it turns out to be positive here, and positive here, and then maybe it's negative here and positive here, and we'll do a specific example in just a minute, I can kind of guess the graph. The graph here is it's positive. Here it's positive again. I have to come down to that 0 while staying positive. Now it's negative, so I'm underneath, and then I'm positive for the rest of the time. I've got a pretty good graph. So it's a simple matter. Get those zeros and then test to see if you're above or below in here. You got a hell of a nice graph. So let's do that together. Let's practice. Okay, so the way our book poses this problem is as follows. And so this is section 1.6. Number 15, it says solve each inequality. And I want to show you, it's just what I was saying here. So this first one is x minus 3 times x minus 2 squared greater than 0. This is just this problem. So notice that we have a polynomial here. It's just a factored polynomial. Factored polynomial. That's awesome. So I'm just going to kind of write it out here, a little scratch work, so that we have it, put it to the side. What are the zeros? What are my zeros? So where does P of X equal 0? When you have a factored form, it's kind of right there. What x values are going to give me an output of 0? What kills off that? What kills off that?
3 and 2.
3 and 2. When x equals 3, this piece is 0. So you just look at the factors and find what makes each of those 0. So, or x equals 2. Does that make sense? How to get that? Everybody cool with that? Let me know. Base, you cool with that? Yeah? So I'm going to come down to a number line. I'll do this in a slightly different way with less drawing. So here we're just going to make a little sign chart. And I've got x is 2 and x is 3, and those are zeros. So I'll just mark them off with circles or something. And now I've got 3 regions to test. Always look for the low-hanging fruit. Zeros and ones and minus ones are just so easy to work with. So here, I'm going to test x equals 0. And I plug that in here. Now watch, I don't care about the actual output value. I just care about the sign. So this will be negative, and this will be -2, but squared, so it's a positive. So when x is 0, I've got negative times positive, I get a negative. And I'm actually under the axis there. Is that making sense? Could you finish that up for me, please? Test a couple more points. You got a funky one you need to do in the middle, and then on the right. And then go ahead and see if you can come up with a graph. Give that a shot. A very rough one. That's all we care about. For a middle point, I would just grab 2.5. You could grab whatever you want though. Anything out of there will work. So you should be getting a negative. It's underneath in the interval from 2 to 3. And it is above on the right. So here it is low, low, above. So if you were sketching out a graph, it probably looks something like this. Below, come up to the 0, below, between 2 and 3, but you have to come up to the 0, and then above. Look at that, we got a decent graph. We understand something about this thing. Can I answer any questions about how I made that picture? Looked like you were fishing back. Like you were doing kind of fishing. We good on that? We can do this? Let's try it. But the original problem was, where is this true? So where is this true? Where is this quantity positive? Can somebody help me out here? Jack, what you
X is
got?
greater than 3.
When X is bigger than 3. So the solution here is X has to be bigger than 3, and I got that through this process. This process. All right, your turn. Let me give you one. So please do the same thing, but for this one. We've got X minus 4 times X plus 3 times X plus 6 less than 0. Where's that happening? Can you get all this stuff? Can you make a rough graph of this critter right here? I'm gonna run to the restroom, I'll be right back. Chat. got zeros at 4, -3. Screwed that up. Let's see here. So 4, -3, -6. Roughly that spacing. Pretty rough. That all cool on the zeros? Fantastic. Now I just go through here and take this quantity and test a point out of each region. So I'm going to test x equals -7. Negative. Negative. Oop. Negative. So when I test x equals -7, all three of these are negative, and that's 3 negatives together. We are negative in this region. So that actually is going to be part of the solution to that inequality. But I also know that the graph lives underneath in that region. Did I do that okay? Anybody get something different? Good? Okay. Nice little sanity check for me. Thank you. And so now here I'm going to test x equals -4. Why not? So I'm going to get a negative. It's -8. -4 and 3 is -1, so that's a negative. And then that becomes positive. So overall, now this is positive in this region. And so the graph must look something like this. You always have to come back to the zeros. So that's how I know this thing has to curve down and come back. It's gotta go through there. Things just don't jump around. At least polynomials don't. And then in here, oh, low-hanging fruit, how I love thee. I will test x equals 0. Negative, positive, positive. And that is a negative. So this is underneath here. And then it's got to come back to the 0. And lastly, test whatever you want. Look, I'm going to test x equals 10 just to make sure it's really big. And then I've got a positive, and a positive. And that's a positive. Sweet. So it keeps on cruising, and I got a decent graph in the process. So the solution to this inequality is going to be this region where it's under and this region where it's under. So the solution is everything from -infinity up to -6. Don't include this -6 because we're 0 there. If this had equal to 0, that would be include the -6. And then I skip over this part and get it up at -3 to 4, and we're good to go. That's a union sign. Or draw a number line and show me where. I don't really care how you express your answers here. This is also a totally kosher and cool answer to me. You draw a number line and you just color in where the solution is. That's awesome too. Or you write a sentence. That sounds painful, but you could. Any questions on that, my friends? I got one last thing to tell you, and that's what happens when we have a polynomial over a polynomial. Actually, it's almost the same kind of process, but we have one little thing to worry about. So here, these things are called rational functions. And what they are is a polynomial over a polynomial. That's it. Same thing. So the skills that we just had, we're going to incorporate into this, and how to get a rough graph. Step 1, find where the numerator, the top, is 0. So find the zeros of the numerator. So you could call this poly top and poly bottom. That sounds weird. I don't like the way that sounds, but it's already up there on the board. So find the zeros of the polytop. That sounds just like stuff like an old dude like me just hears about on TikTok. Number 2. And then plot those. Find the zeros of the bottom. So on top, these will actually be where it crosses the horizontal axis. And the bottom ones represent something different. The bottom ones are where we have vertical asymptotes because we're dividing by 0. We can't do that. So this is where we have vertical asymptotes. So step 1 is find the zeros of the top. Step 2 is find the zeros of the bottom. Step 3 is mark these off on a graph. So what I mean by that is got my X, I got my output, and I'm just gonna mark off the zeros with dots, and I'm gonna mark off the asymptotes with dotted vertical lines. So these are the zeros of the denominator, and these are the zeros of the numerator. And then test the sign of the thing. Just like we did before, pick points out of each of the regions, but there's new regions now. So for example, here's a region between the 0 and the asymptote. Here's a region in here. So I'm gonna put this up here, and it's kind of hard to write out words, but it's the same thing we just did, and we'll just practice a couple times. Then test, so this is step 4, test the sign of the output in each region between zeros and asymptotes. So let's do this. Let's practice. Here's a couple of problems right here. Well, I don't like these, so I'm gonna make a new one. So let's say I've got P of X equals X minus 4 over X plus 1 over X minus 2 times X plus 4. Let's say I have this. I asked you to sketch it. So let's do that. Because with this process, we can actually get a pretty good sketch. There's one little detail that we haven't talked about, and it's a pretty straightforward one. Let's just get this done first. All right, so make an axis. Pair of axes. We got P of X, we got X. I'm gonna mark off the zeros. So I have zeros at X equals 4 and minus 1. Put dots there. I've got vertical asymptotes at X equals 2 and X equals minus 4. So vertical asymptotes at 2 and minus 4. So I mark off those with dotted lines. It's kind of amazing how good a graph we're going to get with very little actual effort. These are just observations. So now, test a point out of each region. and see if you're above or below. You can change sign over these asymptotes. That's why we do it. It could be positive on one side, negative on the other. So here, I'm going to test -5. And I've got a fraction, so on the top, I'm going to have negative times a negative, because -5 minus 4 is -9. -5 plus 1 is negative, over negative, and then this one will also be negative. And what's the end result then if I have 4 negatives involved?
Positive.
Positive, so this equals a positive. So in this side, we are above here I'm gonna put it above. And when I say that, I mean above this horizontal axis. We'll have to figure out a little bit more details before we get that one totally hammered out. Now I've got to test between these 2 points, -4 and -1. So here I'm gonna test x equals -2. And I'm gonna get a negative, a negative, a negative, and a positive. So here we're gonna get negative, 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 positive. And so the net effect is negative. So here I'm below the horizontal axis. Let's get all this done. Could you finish this up for me, please, friends? So we have this region you want to test, this region, and then that final region. Just see, let's go through this with me. I'll go through and check while you're doing it and realize there's an x equals 0s in there, so that's sweetness. Squiggly lines there to just keep the regions between the zeros and the asymptotes kind of clear. Hopefully that's not too messy. Indeed. So let me do a quick clean summary of what I've just done and we can compare. So let's see, so we got a -4. And a -1 there. And then up to 2. 1, 2, like that. And then I got one more 0 and that is at 4. So out here, and here's a couple little tips. When you come towards or leave an asymptote, you have to leave it in a very certain way. So the fact that I'm positive over here and I've got this asymptote means that I have to approach that asymptote like this. So you're always kind of concave away from the asymptote. I don't quite know what happens here. We're going to talk about that in just a minute because something interesting actually happens as I move out this way. But near the asymptote, it looks like that. This one's pretty chill because here I'm below, in this region I'm below. So that means I leave that asymptote concave away from it, and I have to hit that 0. And then I found out I'm positive between that 0 and this asymptote. So that means I come above, and as I approach that asymptote, concave away from it. This graph's looking hella good. Really haven't done anything super detailed. And so then between the asymptote and x equals 4, I am negative. So I'm right by the asymptote below, negative here. And then I become positive. And something else will happen out that way. We're gonna hold on. But damn, that's a good graph. Right? Like pretty good for just guessing. If you just know how you approach and leave asymptotes, you can do something really pretty here. There's one last thing we want to add to our graphs. Last detail. And this is end tail behavior. So let's actually talk about tail behavior. If it's polynomial, it's either, actually, can I stop and just make sure, any questions on how I got what I got? Good. Good on this? Mace? Yeah, okay, cool. So tail behavior. As x gets bigger, and so toward the right, so this is right tail behavior. As x approaches positive infinity, p of x equals a polynomial approaches plus or minus infinity. And you'll know this by how, if its sign is positive in that region, it's going to plus infinity. If that sign is negative in that region, it goes to negative infinity. So this plus minus is determined by the sign. In leftmost and rightmost regions. So that's pretty straightforward if I just have a good old polynomial. If I have a rational function, so I've got a poly over a poly, let's call that poly numerator over poly denominator. Then, here's what we've got, a couple of cases. So if the degree of the numerator is less than the degree of the denominator, the long-term behavior is 0 in both directions. So tail behavior approaches output of 0. So in other words, the graph is going to look something like that. You've got these asymptotes just headed towards 0. Or you've got these asymptotes at an asymptote at 0, and you approach like that. If the degree of the numerator equals the degree of the denominator, like they're both second degree, then the output approaches the ratio of leading coefficients. I'm going to write that out. As x goes to plus infinity, and also as x goes to minus infinity as well. I'm really cramming myself in down here. So I'm just gonna try to, just for completeness, get this in. If the degree of the numerator is greater than the degree of the denominator, then it's gonna go to plus or minus infinity, and you just have to look, is it positive here? It's gonna go to plus infinity. If it's minus here, it's going to minus infinity. So for this last case, output approaches plus infinity or minus infinity. Let's practice. That's it, that's the last little detail. I kind of need to get more calculus-y to talk about what's going on there. And I'm happy to talk about it if you'd like. But let's do a practice with this guy. Oh yeah, let's finish our guy here. Shoot, it was so pretty. Let me put it back. So we had that. I had a 0 at -1. I had an asymptote at 2. -4, -1. And then I had a 0 at 4. So I'm curious, what happens to the graph as I move out this way? What happens as I move out that way? And so what I do is I look at the leading coefficients. What is the first term here? What will be my leading term here when you multiply these out? After you FOIL, what do you get? What's just the very highest power of x? That's all we really care about. Just waiting. What you tell me? Anybody got that for me? What's the highest power of x on top?
2.
Yay! Thank you! Yes! X squared. If you FOIL this out, you get x squared plus other stuff. Thank you. You seem like a lady who knows answers. What do I get on the bottom for the highest power of x? 2. Thank you. So I get here an x squared plus lesser stuff. So the ratio of leading coefficients is 1 to 1. So this approaches 1 over 1, which is these leading coefficients, as x goes to plus infinity or minus infinity. So that means that here I'm going to put a 1, make a dotted line, and that's where we end up as we approach the tail ends. That's it. That's everything I wanted to tell you about this stuff. I think you've got enough to figure it out. Let's try. Let's work on some stuff. And I'll come around and help. Thanks, friends. Maybe I'll come. Let me grab a jelly bean. I'll be right there, Mace.
I fixed kind of the issue.
Did you fix some stuff?
Yeah.
Fantastic.
Yeah.
Does anybody need more time on any of the homework? Do we need any extensions? Happy to do it. Okay.
Maybe after class.
Okay, okay, that sounds good. All right, right on, you're welcome. Oh, you're taking some stuff. That's good. Anything I can help you with? Okay. Thank you for your help. Do you need any help with anything?
No, I think I'm good.
Damn, right on. Yeah. You got that next assignment already knocked out, I saw, so
Yeah.
incredible. I help you with anything.
One left on my
Cool.
I couldn't figure out how to use that for the calculator.
Okay. Let me just get. Oh, okay. Oh, I think that your form of your answer is what's wrong, because they're just looking for the x coordinates. So just take out all the parentheses and the comma zeros. Yeah, I think that's honestly gonna do it. Nice.
I did
So,
that on.
yes, yes.
I did that on this though.
That's
I
great.
couldn't figure out how to do it.
Oh, good, yeah.
I tried to watch the video, but it's been.
That's cool.
forever since I've
And you
done
can
it.
use this during
Okay.
exams and whatever if you want to,
I
because
really got confused.
Desmos is way better.
Okay, it was a little bit more accurate, like.
I agree.
Okay.
Yeah,
Yeah,
cool,
that's easier.
well done.
Thank you.
Feel free to leave if you need. Do as you see fit, my friend. Hi, how are you doing? You doing good? Everything rocking?
Yeah, just finishing up this one.
Cool. Nice. Oh yeah, see you Monday. Don't forget, no class on Wednesday. I'll put a video up.
Okay.
Enjoy.